Hi everybody, welcome to my 8th video on axial bars. In this video I'm going to be working through this example you see here, finding the internal normal forces and the corresponding displacements. If you want to know something else about axial bars, feel free to check out any of my other videos about axial bars. Alright, let's get right into this. In order to find the internal displacements, we need to find N, all the internal forces. In order to do that, we need to make cuts every time there is something that changes in our axial bar. So we start here and take a look. In this section here, A, E, and internal force are going to be constant. So we can make a cut anywhere along here. Alright, so we'll call that there cut 2. And as soon as we get to this piece here, the area changes. The force inside will change because we have this 90 here, and the E, the Young's modulus, changes. So we need to make a cut here as well. Alright, so let's make free body diagrams of each one of these cuts. So we'll start with the second one. And 20 newtons pulls here. And of course we're going to have an internal reaction, N2. Don't forget to label your directions. This makes it clear for somebody who's reading or proofreading your work to know what you mean when you say the sum of the forces in the x equals 0. It's all about process. N2 equals 20 kilonewtons. Box it off. Indicate where you can find it. Alright, free body diagram 1. So this one is this whole piece here, thick and thin piece. Let's draw a little representation of that. Just like this. And on this piece we have multiple forces acting. We have 20 kilonewtons here. And there we have 90 kilonewtons. And don't forget, at the cut, there's going to be some sort of internal reaction resisting these two. And 1. So the forces in the x equals 0 once again. 20 minus 90 minus N1 equals 0, therefore N1 negative 70 kilonewtons. N1. Alright, let's plot these. So the bit in the first piece that we called 1, negative 70. And it's constant throughout that piece. So the line that I draw is just going to be straight. Negative 70 kilonewtons. And in the second piece, it jumps up to 20. Alright, now if you notice, the distance it jumps is the amount that this force here is. Alright, and that totally makes sense. Because the only reason it changed is because of that force. So it would only make sense that the amount that it changed was the magnitude of that force. There we go. Alright, so let's move into finding the displacement of this bar. So we know the displacement, total, is going to be the sum of the displacements of each piece. So we can calculate the displacement of this piece, the displacement of this piece, and add them both together. Using the equation that we should be familiar with is NL over EA. And we don't need to use the differential form because the areas are constant. However, we could use it, and we could integrate, but we'd just be integrating a constant all the time, and that just makes it complicated. So it's delta 1 plus delta 2. Each section has its own elongation. And of course, the elongation of section 1 is due to the normal force in the first piece, the length of the first piece, the Young's modulus of the first piece, and the area of the first piece. The same goes for the second piece. N2, L2, E2, A2. So now we plug in the numbers that we found for these. The total is N1. N1, negative 70 kilonewtons. Now I like to put in terms of the fundamental units. By fundamental units, I mean meters, newtons. Don't keep it in terms of kilonewtons and millimeters or nanometers or whatever you're working in, because then you need to figure out, well, what is a meganewton per millimeter? It's best off just to put it in terms of newtons and meters. You get your answer in meters, and from that meters you can change it into any other form that you like. The length of the first piece, 1.5 meters. All right. The E of the first piece, 10 GPa. So that looks like wood. 10 times 10 to the 9. That was the area of the first piece. And it's really nice, this question. It gave us the area instead of just a diameter. 0.5. Plus N2, that's 20,000 times the length, 1.2. Over the E of that piece, that's 70 GPa. Looks like aluminum to me. Times the A of that piece. All right, there it is. 0.005. 0.05. All right, total elongation. All right, so the first bit, delta 1, the elongation is negative 2, 10 to the minus 5. The elongation of the second piece, 6.86, 10 to the negative 6. All right, now we can rewrite this as 0.686 times 10 minus 5. All right, that makes it easy for us because then we have everything in terms of 10 to the negative 5. And the total delta, the total displacement, so therefore the very end of this bar has moved the sum of these two. So negative 1.41 times 10 to the minus 5 meters. All right. All right, now let's plot these. So to kind of get an idea of what the elongation will look like, let's quickly plot what the E's are. So the E for the first section is 10. The E for the second section is 70. So it goes from 10 up to 70. The area, we have quite a bit of area here, 0.5. And in the second piece, it jumps down to 0.05 meters squared. So we know a tenth of the previous value. All right, so the elongation's NL over AE. So for the first piece, N is negative. So we know that the whole works is going to be negative unless E is negative and A is negative. That's never going to be the case. You never can have a negative area, and you can't have a negative Young's modulus either. So you know the first piece, it's going to be getting scrunched. It's going to be getting smaller, so it's going to go down here somewhere. All right, now E times A of the first piece is about the same as E times A of the second piece, just looking at these graphs. But we see here that now this is positive and it's much less. So we know the slope is going to be positive, and it's not going to be, in terms of magnitude, as steep as the other slope. So we expect it to go negative and then up again with a gentle slope there. So let's just plot that. At the origin, of course, nothing happens because, when it's fixed to the wall, it's not moving. The delta at 1 is just this, which is that, which is that. All right, I'll put it down here, negative 2.1 times 10 to the minus 5 meters. All right, it goes like this. Increases in a linear fashion. Okay. And then this piece here is under tension, right? Because we have a positive force. So that's getting longer by an amount this much longer. So the amount here plus this much equals to the total elongation, negative 1.41 times 10 to the minus 5 meters. There we go, just as predicted. So that's why I like to draw these graphs here. Of course, you don't have to do that, but I like to do that just to explain it better. Alright, so here's an example, and just following the general method that I've been following so far. You draw a clear initial picture, make sure you have all the information you need. You draw a free body diagram of each piece, clearly label it. You find an equation for the total elongation. It's the sum of all the elongations of each separate piece. You recognize that each elongation of each separate piece is due to the properties of that piece. You plug in all your numbers. You get a bunch of separate values for the elongation, so it's easy to solve for each point. You add it up, and you graph it. Alright, I hope this video helps. Thanks so much. I'll see you next time.